Hello. In the previous two videos we have discussed at length what can be done with ergodic Markov chains. We have also explained that ergodic chains do not have transient states. One might thus be tempted to assume that Markov chains with transient states are useless, that we cannot predict anything if we are given a Markov chain with transient states, and that as such they cannot be used to model phenomenon. The aim of this video is to convince you that this viewpoint is wrong, and in particular to show you how we can calculate hitting times and hitting probabilities for Markov chains that have a combination of transient and recurrent states. Key to this will be two results from previous videos: the partition theorem and the condition expectation theorem. As such, if you have forgotten about these ideas, look them up before watching the rest of this video. You could even watch the videos where these ideas were first introduced one further time, before watching the remainder of this video. Now, before I go on, I want to issue a little bit of a disclaimer. In this video, I am not being as mathematically rigorous as I could be with some of the proofs. If you work through the corresponding worksheets, they will take you through all the mathematics with the appropriate degree of rigor. Similarly, the detailed notes take you through all the mathematics presented in this video with an appropriate degree of rigor. The reason for my lack of rigor here is that the important thing in this video are the final results. You can get through the examination paper by memorizing the formulae for the hitting time and hitting probabilities. What is important is understanding what is being calculated by these formulae and knowing how to use them. Having said that though, the proofs are not difficult and will perhaps appear easier for you to work through once you have watched this video and got a flavour of the mathematics involved. Without further ado then, let's move on and remind ourselves about transient and recurrent states in Markov chains. Look at this transition graph and work out which states are transient and which states are recurrent. Pause the video and take a moment to do this for yourself. Okay. So hopefully you were able to work out that states 2, 3 and 4 are transient because once you leave them, there is a finite probability that you will never return to them. This is because once you leave states 2, 3 and 4 and go to either state 1 or state 5, you are guaranteed to remain in these states forevermore. States 1 and 5 are recurrent as a result. Now there needs to be some precision in what we are saying here. Notice that I always state that a state is transient if there is a finite probability that when you leave these states, you will never return. This is important. A state is not transient by virtue of there being a finite probability that it will not be visited. There is a finite probability that the system will never visit state 1 here, and yet this state is still recurrent. The point here, though, is that if you never visit state 1, you cannot return to it. You thus cannot have a path that begins and ends in state 1. You thus never generate an instance of the random variable R1, the return times the state 1. State 1 is thus still recurrent. Let's move on and consider what we can predict when we are presented with a Markov chain like the one shown here. Consider the limiting behavior of this chain. We know that the system is going to eventually end up in either state 1 or state 5. If you are not convinced, reconsider the ideas in the video where we introduce these definitions of transient and recurrent states. We thus might want to predict one of two things. We might want to know the probability that we will finish in state 1 as opposed to state 5. That is to say, we might want to know whether we are more likely to end up in state 1 or state 5. The second thing we might want to know is the expected number of steps the system will take before it ends up in state 1 or state 5. In this video, we are going to learn formulas for calculating both these quantities. We will find that the probability that we finish in each of the various states are given in a matrix, as the probability of ending up in state 1 here will depend on whether we start from states 2, 3 or 4. Furthermore, on starting from each of these states, we will have a probability of finishing in state 1 and a probability of finishing in state 5. The expectation, by contrast, the expected hitting time, by contrast, will be a vector, as when we are calculating this quantity, we are not calculating a conditional expectation, like the expected time until you leave the transient states, given that you finish in state 1. No, what we are calculating is the expected number of steps until absorption in either state 1 or state 5. The first step in the calculation of the matrices of hitting probabilities and vectors of expected hitting times described in the previous slide is the writing out of the transition matrix in a particular way. What we would like to do is order the rows of the matrix such that all the transient states are above the recurrent states. Similarly, when writing out the columns, we would like to arrange them so that the transient states appear to the left of the recurrent states. When we do this for this example, we find that the first 3 rows of the matrix and the first 3 columns of the matrix will involve the transient states, states 2, 3 and 4. And that the last 2 rows and the last 2 columns will involve the recurrent states, states 1 and 5. When the matrix is written out with these states in this order, we can divide it into 4 parts. In the top left corner of the matrix, there is a square matrix that we call Q. The probabilities in this part of the matrix describe all the probabilities of transitions between pairs of transient states. The top right part of the matrix is rectangular. We call it R. The transition probabilities here tell you about the probabilities that there will be transitions from transient states that finish in recurrent states. In the bottom right part of the matrix, you have all the probabilities of transition from recurrent states to transient states. In this example, these would be the probabilities for transitions between states 1 and 5 and states 2, 3 and 4. These probabilities are all 0, because otherwise the transient states, states 2, 3 and 4 in this example, would not be transient, as there would be a finite probability of returning from states 1 and 5 to states 2, 3 and 4. The last part of the matrix, the bottom right corner, is again a square matrix. For the graph shown here, this part of the matrix is the identity, as state 1 is only connected to itself and state 5 is only connected to itself. Now, this part of the matrix could be more complicated, but it won't be in the exam. It will always be the identity matrix. Even if it were more complicated, however, the method for solving these types of problems would still essentially be the same. The reason for partitioning the matrix in this way is that we only need the Q and R parts of the one-step transition matrix in order to solve the problems outlined on the previous slides. Let's briefly remind ourselves of the first of these problems. In this case, we know that states 2, 3 and 4 are transient and that the system is thus bound to leave these states forever at some stage in the future. What we would like to be able to predict is the probability that when we do so, you finish in either state 5 or state 1. In other words, we want to know whether you are more likely to end up in state 5 or state 1. How do we do this calculation? Well, as it turns out, it is relatively straightforward. We just use the partition theorem that we learnt about during previous videos. When using this theorem, we condition on the first step in the chain. So the random variable capital X here is the state that we arrive in after the first step of the chain. The random variable Y, meanwhile, is the state that we finish in. So either in this example, either state 1 or state 5. Now here is the part where I could perhaps write all this out more carefully. It is dealt with in detail in the notes, but here I'm just going to give the final result and explain where it comes from. This result is as follows. Our hitting probability matrix, capital H, so the matrix of telling us the probabilities of finishing in state 1 and 5, given that we start in states 2, 3 and 4, can be calculated as Q multiplied by H plus R. Allow me to explain where this result comes from. Remember, we are conditioning on the state that we arrive to after the first step. There are two possibilities here. Either the first step takes us directly to a recurrent state, and the probabilities that these occur are in the R part of the above matrix, the part of the matrix that describes probabilities between transient and recurrent states. To be clear, the R appears as the P x equals I part of the partition theorem. As if we arrive in a recurrent state, on the first step, the conditional probability that we will remain in that recurrent state forevermore, Py equals 1 given x equals I in the partition theorem, is just 1. As in the above graph, there is no way to get anywhere else once we arrive in state 1 or state 5. This explains the factor of plus r in the above formula. What about the factor of q multiplied by h? Well, to understand this, you simply need to remember two things. First of all, that the q part of the transition matrix describes transitions between pairs of transient states. The factor of q thus represents the absolute probability part of our partition theorem that tells us the probability that our first step is from a transient state to yet another transient state. Notice that this is in contrast to the term we have already examined, the plus r, which came about by considering what the probability would be if our first step was from a transient state to one of the recurrent states. The second thing to remember is that our process is Markovian. As such, the only thing that determines the future behaviour of the system is the present state of the system. Consequently, when we calculate the conditional probability of finishing in a particular recurrent state, given that our first step was from one transient state to another transient state, we do not need to recall the state we were in before that first step transpired. We need only consider the state we arrived in once the first step was completed. This is where the factor of h comes from. If our first step is to a transient state, what happens after is completely determined by the transient state that we find ourselves in. Now, there were a lot of words in that explanation, and I will perhaps confuse you if I say more. It is much simpler than it sounds, however. The whole thing is just a relatively straightforward application of the partition theorem that we learnt about in a previous video. Now let's say we want to determine the matrix of hitting probabilities, capital H. Rearranging the formula that we have just arrived at, we find that H can be calculated as follows. Here notice that I is the identity matrix. Before we continue, let's digress for a moment and consider some pretty cool maths that makes this all rather convincing. The first step in doing this is to recall the following result on power series. In essence, if we take a number a that is less than 1 and take the sum of all of the integer powers of a, this is equal to 1 minus a all to the power minus 1. In other words, it is equal to 1 over 1 minus a. The cool thing is that a similar thing holds for invertible square matrices. If we take the identity matrix, subtract an invertible square matrix Q from it, and then invert the whole result, we find that this is equal to the identity plus all the various powers of our matrix Q as shown here. Why do I mention this? Well, let's substitute the factor of I minus q to the power of minus 1 in our hitting probability formula by the power series of matrices shown here. We get the following result. That is, H is equal to R plus Q multiplied by R plus Q squared multiplied by R, and so on. Now consider this result in the context of the Chapman-Kolmogorov relation. This relation tells us that we can calculate the n-step probability matrix of a Markov chain by taking the nth power of the one-step transition probability matrix. What this formula is saying is that we can calculate the probabilities of ending up in each of the recurrent states by adding the probability that our first step is to a recurrent state to the probability that we take one step to a transient state and then move to a recurrent state, this is equal to QR, to the probability that we take two steps through the transient states and then move to a recurrent state, this is equal to Q squared R, and so on. I think this is cool. Many of you probably consider this makes me sound completely insane, so coming back to the topic in hand, let's be totally clear on what the final result from the calculation that we have just introduced is equal to. When we take the matrix I minus Q and invert it and multiply it by R, we get a rectangular matrix. The number of rows in this matrix is equal to the number of transient states, while the number of columns is equal to the number of recurrent states. For the example shown here, we can thus label the rows 2, 3, and 4, and the columns as 1 and 5. If we look at the elements of this matrix, they then tell us the probability that we finish in a particular recurrent state, given that we started in a particular transient state. So for example, the first example shown here gives you the probability of finishing in state 1, given that you started out in state 2. The second example, by contrast, is the probability that you finish in state 5, given that you started out in state 4. Notice here that the order of states in the rows and columns of the matrix is the same as the order we put them in when we constructed our one-step transition matrix that was divided into Q, R, and so on. Let's now turn to the other calculation that I promised at the start of this video, the expected hitting time. The object we will obtain when this calculation is completed will be a vector as opposed to a matrix, and let's briefly consider why. As we have already discussed, when we generate a Markov chain using this transition matrix, we are guaranteed to eventually leave the transient states 2, 3, and 4 forever, and to eventually end up in one of the recurrent states 1 or 5. So we'll leave the 3 transient states and we'll end up in one of the recurrent states 1 or 5. We have just discussed how to calculate the probability that we end up in state 1 as opposed to state 5. In general, what we now want to calculate is the expected time until absorption in state 1 or state 5. In general, the expected time till absorption in a recurrent state. Why is this the expected time to absorption in state 1 or state 5 and not the expected time to absorption in state 1? Well, we might never reach state 1. If we arrive in state 5 first, we will certainly never get to state 1. This is a problem as we cannot calculate the expectation of a random variable if the probability that it is less than infinity is not equal to 1. We thus have to calculate the expectation of the only random variable that we know is guaranteed to be less than infinity, the random variable that measures how many steps there are before absorbing in either state 1 or state 5. When we calculate our expected hitting times, we thus obtain only one number for each of the transient states, the expected time until absorption in a recurrent state, given that we start in each of the transient states. For the graph shown here, this is a 3-dimensional vector, as there are 3 transient states. With that settled, how then do we calculate these hitting times? Well, as with the hitting probability, the key thing is to use a result that we have learnt about elsewhere. This time, that result is the condition expectation theorem. Here, once again, we condition on the state we arrive in at the end of the first step in our Markov chain. In this expression, we use the symbol capital X to denote this particular random variable. Now, much as we did for the hitting probabilities, we consider that there are 2 possible things that might happen during the first step. The first of these 2 things is this initial step takes us directly from the transient state to a recurrent state. The second is that the first step takes us from one transient state to a second transient state. The final result, when we consider these two possible outcomes, looks like this. The first term here comes from considering what happens when our first step is from transient to transient, while the second term here comes about from considering what happens when our first step is from transient to recurrent. This is why factors of Q and R appear in these two terms respectively. The bold-faced capital 1 that appears in these two terms indicates a vector of all ones. For the second term, this 1 indicates that if our first step is to a recurrent state, the time to absorption, and hence the expected time to absorption, is just 1. In the first time, by contrast, this 1 is added to the hitting time vector because we have taken one step, but the process is Markovian, and thus what happens after this first step is independent of what came before. The first step in simplifying this expression is to multiply the matrices of Q and R by the vectors of 1s. This is equivalent to summing the elements in each of the rows of the full transition matrix. We know what these sums of the rows are equal to, however. They are simply equal to 1. We can thus replace the factor of Q multiplied by 1 plus R multiplied by 1 by 1. This brings us to the expression shown here, which we can rearrange to get the following formula for the hitting probability vector. The dimensionality of this vector will be equal to the number of transient states in the Markov chain. Furthermore, each element will represent the expected hitting time given that you started from a particular transient state. To conclude then, we have in this video introduced two formulae that can be used when a Markov chain has a mixture of transient and recurrent states. The first of these calculates the hitting probabilities, that is to say the probabilities that we finish in each of the recurrent states, given that we started in particular transient states. The second, meanwhile, calculates the expected hitting times, that is to say the expected time until absorption in one of the recurrent states, given that you start in a particular transient state. We have gone over the proofs of these two formulae, but you should go through the worksheets and notes in more details if you want to fully understand them. In terms of using these things in practice, the most important things to understand are what are being calculated by these two formulae and the way in which the matrices and vectors that you obtain by applying them should be interpreted. You will have the opportunity to study this by doing worked examples in the lecture and in tutorials. So that's enough for now. Thank you.